information about A and B, doesn't matter which one we choose. I'm just going to choose something to get ourselves started. And now, 1 is an existential. You do existentials as soon as you can because it gives you a new letter. And once you've got that new letter, you can use it for other things. So there exists something. It may be A, it may be B, but just in case we've got a new name, if it turns out to be the same as one of the existing letters, we'll just say C equals A or C equals B because we can do that in our new language now. We've got identity, we can say things are equal. So it's always safe to use a new letter because we can say it's equal to an old letter if we need it. This is why it's safe. So there is something, we'll call it C, 6. So this will be for all y, f of y, if and only if y equals C, which is our new letter. That's from 1. And we're getting rid of the existential. So we've got this rather annoying rule where you've got to go down the bottom and say this is the thing that's getting rid of the existential from 1. We're doing this by this block of reasoning 7 to 8, existential elimination. Right, on the same thing that we had before. There are very similar systems that don't mean you have to do this. They've got a slightly different complicated rule for checking variables, which I much prefer. Okay. So now we've got our C, we've got our A and our B. What do we do next? Well, we've got either A is a frog, in which case we don't know whether it'll be green or not, but we know that B has to be green if it's not the same as A. So we'll reason with that. And then similarly, we'll say if A is green, then we're done. If A is green, then A is green or B is green, which means A is green or B is green or A equals B. So if G of A, then we're pretty much done. So we need to concentrate on F of A. So let's just do G of A because we can do that. We assume G of A, and we can get what we want. And then we'll do the hard case, which is F of A, and we'll try to prove what we want. And that means we'll get rid of 6 here, through 9 to 10, and 11 to 12. 9 to 10 is one block of our reasoning, and 11 to 12 the other block of our reasoning. And that's the only way you can eliminate a disjunction, is by going through all the cases. Okay, so we've got G of A. We've got G of A, we're trying to prove GA or GB or A equals B. This is going to be repeated disjunction introduction. G of A, so G of A or G of B, which means G of A or G of B or A equals B. Let's put the numbering in. But if we assume F of A, which is the other half of our disjunct, now we've got some information. A is a frog. And that might help us to tell what's happening with the colours or whether A and B are the same. Now, what do we know? We've already got this thing here we haven't used yet. Everything, it's a frog if and only if it is C. And we know A is a frog, so let's put that in. A is a frog if and only if A equals C. This is from 7. And that looks useful because we've got 11. That's why we chose the A there. A is a frog, it's a frog if and only if A is equal to C. Don't know what I want to use it for, but it's trying out to do that, so I'm just doing it. A is that frog we were talking about, which is good because we see there was only one frog. So that comes from 11 and 14. We got rid of our double-headed arrow. So A is a frog. Now, what about B? We don't know whether B is a frog yet or not. That's problematic. But we do know that B is a frog or B is green. Because everything is either a frog or green. So if we just scroll back up again, everything is a frog or green. A little information about A, we'll do the same for B. 16, this comes from 6. No, 6 or 2. 2, universal elimination. We'll do the same sort of thing again. So, if G of B, then G of A or G of B to this, so that's going to be an easy case. If not, we're going to have F of B. We're going to have F of B and F of A, and then hopefully we're going to know that they're the same frog because there's only one. Then they'll be equal to each other. So that's the next sort of stage we're going to be doing. Okay, so again, G of B is an easy case, so let's just do that. G of B, so G of A or G of B, so G of A or G of B, or A equals B. That's structure, Andrew. 17, 18, 19, 20. We're doing a disjunction elimination on 16 through 17 to 18 and 19 to 20. So either G of B or F of B. Either way, we're still trying to prove the same rather annoying and long disjunction. If we assume G of B, then we introduce a disjunction from 17 and then from 21, and we get the answer we want. The only interesting case we've got left is F of B. So we know F of A, we know F of B, and we need to prove that either that one's green or the other green, or that they're equal to each other. And we know we want to prove that they're equal to each other because there's only one frog, which is what our first premise was. Okay. So what did we do for A? We said F of A is a frog if and only if it's equal to C. Same rule applies here. This comes from our first line, going up to our first line. Oops, breaks down to 7. Everything is a frog if and only if it's equal to C. 21. I seem to have miscounted. Ah, 22, thank you. Thank you. We already had a 21. So now, we know B equals C, because F of B, and if F of B, then B of C. So we're still just unpacking rules without much plan. We're just breaking things down and seeing what happens. So that's 19 and 22, and double arrow elimination. So we have A equals C and B equals C. And from that, we can prove A equals B, because one of the C's will be changed to one of the letters depending on which one you choose. So we want 15 and 23. If two things are equal to each other, if two things are equal to the same thing, they're both equal to C, so they're equal to each other. That's the transitivity we proved, which is really just one step anyway. So now we know A equals B, and from that, A equals B, or whatever we damn well feel like. So if there's only one frog, and everything is green or a frog, then either this is a green, or this is a green, or we're talking about the same thing. Not quite the biological conclusion that I wanted, but this is a slightly larger proof, which does depend on identity quite often. But we only used an identity rule once. We used identity statements quite a few places to maneuver with them. We only needed one or two identity rules.